In section 2.7, we're going to look at variation. Specifically, we're going to look at direct variation, inverse variation, and then joint and compound variation. Let's go ahead and start off with direct variation. In direct variation, we say one quantity, which we'll label as y, is said to vary directly to another quantity, x, or is directionally proportional to x, if there's some constant k such that y equals k times x. This constant k is called the constant of variation and the constant of proportionality. The basic idea with direct variation is that as x increases, we see an enlarging of y as well, whether it's in a positive or a negative direction. Generally, the idea of direct variation, as x is increasing, we tend to see y increasing as well. Unless k was negative, then we would see y decreasing at in a direct way. Specifically in direct variation, with this formula, y equal to kx, k, and this is true of all the variation problems, not just direct, but k is kind of like our adapter value. K will adapt a relationship that is a direct variation relationship to that specific situation. So k will be a number, and we have to figure out what that number is because they will give us a direct variation example, and then we will apply that number into this formula and then usually use it to find out another quantity of y for a different quantity of x. So let me make that a little bit clearer by going through an example on this next slide here. So here we're asked, over here, suppose y varies directly as x and that y equals 20 when x is equal to 4/3. Find y then when x is 8. So a couple things that I want to point out in this problem. This will be kind of a constant thing that you'll see in these direct variation problems is, first of all, it should give you the type of variation that we're dealing with. And in this case, it's direct variation. So we say y varies directly as x, and then typically they're going to give you an example. So the second part here, y equals 20 when x equals 4/3. This is our example scenario. And we're going to use this to find k, which will adapt the direct variation formula to that specific situation. So in step one, since we know it's a direct variation, I know it's y equal to kx. And then, so this is step one. I just write the formula. Step two, let's adapt it to this particular situation, knowing that y is equal to 20 when x is equal to 4/3. So I put those values in for x and y. Again, this is a temporary substitution simply for the purpose of finding out k. And so now what I want to do is to solve this for k. So I'm going to multiply both sides by the reciprocal of that fraction. So 3/4 is the reciprocal. And I don't know, I got that line in there again. We love those lines. And so 4 will go into 20. I think 20 over 1, 4 goes into 25 times. So that leaves me with a k value equal to 15. Here they canceled out top and bottom, so I simply left with k. So the formula adopted to this situation is y equal to 15x. So this actually is my step 3 here that I did on the previous page. Go ahead and put in the value of k, which adopts this direct variation formula to this specific situation. And then step 4, we're going to use this formula to answer the second question that was posed, which is really the ultimate question that was posed. It's on the previous page, but it said to find y when x was equal to 8. And so now that we have this formula, this is a simple one-step thing. We're going to plug in 8 into for x. And so y is equal to 120. So that takes us through that 4-step process of solving a direct variation problem. So let's take a look at a direct variation problem which is connected to a real-life situation. Again, we want to look for some key things. What type of variation we have. Where is the example that we're going to use to find k? And then finally, once we have our equation adapted to this situation with the k value found, let's solve the ultimate part of the question, which is what is x when y is k, or what is k when y is x? One of those two. Okay, so in this problem, we have a electrical circuit. It says the current in a circuit connected to a 220-volt battery is 50 amps. If the current in this circuit is directly proportional to the voltage of the attached battery, what voltage battery is needed to produce a current of 75 amps? So, first things first, what type of relationship do we have? Well, we have a direct proportionality according to this. Direct proportionality, which is the same as a direct variation. Okay. And then, so I know I have a direct variation. Step 1 is to write that out. So we have, in this case, volts being, let's see. Oh, the current is directly proportional to the voltage. So here we're going to let I equal the amps, or that's the current, and V will be the voltage. And so I, or I think that's actually supposed to be a L, is equal to K times V. And I knew that because it kind of said that directly. It said the current is directly proportional to the voltage. So voltage belongs over here with the K, and L belongs on the other side. And then we go to our step 2. I'm going to go ahead and write this in here. Step 2 is we want to find K. So I'm going to use basically the example they give me, where we have a 220-volt battery that is producing 50 amps. And so substituting those in there, I have 50 equaling K times 220. And we solve for K, so divide both sides by 220, which gives us K equal to 50 over 220, or if we cancel out, divide both top and bottom by 10, 5 over 22. Even if you don't adapt it by, or if you don't reduce that fraction, that's not a huge deal. It's not going to give you a wrong answer. Now we go to step 3. In step 3, we want to just put that value in there. So L equal to 5 over 22 V, as in voltage. And then for step 4, they wanted us to find the voltage if 75 amps was my current. So I'm just going to write that in here. And so here they're actually giving us the Y value, right? The dependent value. So you want to pay attention to what is what in these problems. They don't always necessarily give you the X. And what we need to find here is the voltage. And so I'm going to multiply both sides again by the reciprocal, 22 over 5. No matter where I write that, because it's all multiplication, we can cancel these out and we're left with V. And I can take 5 into 75, because 5 goes into 75 15 times. So I'm going to cancel that out. And so then we're left with 15 times 22, which is 330. And in this case, this is a voltage. So the part of step 4, when we actually do the solve, is we want to make sure we're not just getting a number, but we're explaining what this number means. And in this case, for a 75 amp current, we would need to produce 330 volts. Something to that effect, right? This is what we're trying to find, and this is what we found. And you'll notice that on both of these, and I'm going to page back through the other ones, that we started out with the 50 is 220. 50 was 220. And then as we increased the amperage up to 75, volts also increased. That's typical of a direct variation. Also in this one, our original one was saying y was 20 when x was 4/3. And then the question was, well, what's y when x is 8? So x is much larger, it's 8. And with that direct variation, we saw y is equal to 20. So as 120, sorry. And so as x increased, y increased, and as you could look at it in the other direction, if x decreased, y would decrease. So they're basically going in similar directions. And the only difference would be if k there was negative. If k was some sort of negative, as one is going up, the other would come down, or go down in value. But that's still, as one is becoming larger, the other would be getting larger, but in a negative direction. We can also have direct variation, but with powers as well. So y, you want to pay attention and see if you can hear that in a question. A quantity y varies directly as the nth power of x, means that y is equal to k x to the n. So now we just have introduced another part of this, which is it's going to make it increase even more quickly. And k, of course, is a non-zero, so not zero, constant. And n, the power, is greater than 0, meaning it's not. Negative powers, if you recall, would actually put x in the denominator, which is a completely different relation, which is coming up next. So another example here, solving a problem involving direct variation but with power. Suppose you had forgotten the formula for the volume of a sphere. Imagine that. But we're told that the volume V of a sphere varies directly as the cube of its radius. In addition, you're given that V equal to 972 pi when R equals 9. So here's our example that we're going to use. Find V when R is 6, and then here's the ultimate question we want to answer. So with K being something we want to adapt to this problem, we first have to write this out. So volume, we're told, varies directly to the cube of the radius. So here's our K, and we'll use R for radius, and we'll put cube there as the cube. Okay. So we have step 1 taken care of. Step 2, let's use the example they gave us to find the value of K. We're told that volume is, let me go back here, 972 pi when R was equal to 9. So putting those in there, we're going to use this to find my K, 972 pi. That's times pi, by the way. And R is equal to 9. So 9 cubed. Let's go ahead and cube 9, see what we get. Well, 9 cubed is 729. That's 9 times 9, which is 81, and then 81 times 9, 729, and that's multiplied by k. So I have 972 pi equals 729 times k. So we'll divide both sides by 729 to get k by itself. Now, you may not know this right away, but 972 over 429, that can be reduced, and it actually reduces down to 4/3 pi. And most calculators, if you put in 972 over 729, you can reduce that down and see what the reduction is. But it's 4/3 pi. Again, not critical necessarily that you get that into lowest common denominator, but at least you can see that here, because I knew it was some smaller number. I forgot what the formula was. Yeah, things like this you can always look up. So regardless, this is my k, so we'll go to the third step here, which is to substitute that in there. So volume is equal to 4/3 pi times r cubed. And now we want to go to step 4 and to actually solve this for the given problem, which was to find v when r was 6. So now it's just simply a matter of plugging this in. 4/3 times pi times 6 cubed. We can type this into your calculator directly and get a decimal approximation. So 4/3 times, and we can use 3.14, and then times 6 to the third power. And approximately we get, 904.32. And this is the volume of something, of a sphere. So we would say units cubed. I'm not sure they gave us units. Let's go back and check it out. They didn't really give us units. Like, they didn't say it was centimeters or feet or inches or millimeters, or we have no idea what units they were using. But it is volume, and volume is cubic, meaning 3 dimensions. So we're looking for, in a sphere, how many 1 by 1 by 1 cubes, sorry, that's a horrible looking cube, but 1 by 1 by 1 cubes would fit into that. And we'd say it's about 904 little cubes would fit into that sphere, whatever the units are on that. And that's with a radius of 6. So from the center of the sphere out to the edge would be 6 units. So if this was inches, we would say inches cubed, or cubic inches. The next type of variation we want to look at is called an inverse variation. And the one way that or a couple ways we can word this, a quantity y varies inversely as the quantity x. So instead of directly, it's inversely, or we can say y is inversely proportional to x. And with that, instead of k times x, we have k divided x, giving us a rational equation here with with x in the denominator, and k is just a non-zero. We say these have to be non-zero because if that was 0, we would have just y equaling 0. So you really wouldn't have any kind of inverse or direct variation or any kind of variation at all. So just has to be something other than 0. It can be positive, it can be negative. But in general, with inverse variations, we're seeing the opposite occur in our relationships. As x increases, y will tend to decrease. Because as x gets bigger, we can see that's in a denominator, which is going to decrease the value of y. So it's kind of an opposite type of relationship in terms of as one gets larger, the other decreases in size. So taking a look at an example, suppose y varies inversely as x, and y equals 35 when x equals 11. Find y if x equals 55. So I know I have an inverse relationship because they say it right here. So it's pretty straightforward. Y equals k over x. And step 2, let's adopt k to this particular situation. So we know that y is equal to 35 when x is equal to 11. So we'll substitute those in. And then we want to find and solve for k. So I'm going to multiply both sides by 11, canceling this out over here and giving me 11 times 35, which is 385. So my function, or sorry, not my function, but my equation here is y equals 385 k over x. And now we go to our last part, which says find y if x is 55. So I'll write that in here. Find y when x is equal to 55. And so we're just going to go ahead and put that in here. 385 over x, or in this case 55. And we carry this out. This is direct. We don't even have to move anything to the other side. 385 divided by 55 is approximately, well, actually not approximately, it's exactly 7. And we don't have any real context for this problem, so y equaling 7 is straight up the answer I can leave for this problem. We can also have inverse variation, just like we do with direct variation, with powers. So a quantity varies inversely or is inversely proportional as the nth power of x means that y is equal to k over x to some power n, where k is a non-zero, can be 0 but can be positive or negative, constant, and n is greater than 0, so n is a power that is not negative. Okay, so the intensity of light varies inversely as the square of the distance from the light source. If Rita doubles her distance from a lamp, what happens to the intensity of the light in her new location? So this is a little bit interesting, the way that they've worded this. We can tell that this is not just a normal inverse problem because we don't really have a example for us to use here, but we're being asked in general what happens to the intensity if our distance from the lamp is doubled. Well, first of all, let's just go ahead and write out what this would say. It varies inversely, so we know this is an inverse, but inversely as the square of the distance. So we're just going to say I for intensity. I is my intensity. And D we'll say is distance from the light. And then using that, I equaling K, which we're not going to be able to find, but we're going to put down here D and square. We know that's the formula that we have here. Now, the next step of this problem is asking us to double the distance. So let's assume D equals our current distance. And if we want to double that, we would just multiply this by 2. So 2D would be double my current distance, whatever current distance is. We're not told what the distance is, but it doesn't matter. With a proportional relationship, double the current, distance. We should be able to see a pattern with what happens if we double the distance. So I'm gonna take this and let's see. We're gonna just leave K as K because we're not given any numbers here. But I am told that I'm doubling the distance. So I'm going to put 2D in as my distance. Notice I'm putting it in the parenthesis because we want D, my distance, to be squared. So if that's double, that part, including the 2, needs to be squared. And if I simplify that out, that's 2 squared 4 and then D squared. And so we can kind of look at the comparison here between what I have here. Use a different color here, but the coefficient of k is 1 and d squared is 1. So this is my original intensity. And then when I doubled the distance, my coefficients changed a little bit here. I have 1 still with k, but d now has a 4 in front of it. And so that's interesting. This, if we think of this as where we started, right? Whatever k is and whatever d ends up being, I'm going to take that d squared and it's going to get multiplied by 4 in the denominator. And so you'll notice there that it's 1/4. So the question here was, what happens to the intensity of light at her new location? Well, we can see that no matter what the distance is, it's kind of irrelevant. Once you have doubled the distance, the intensity of the light will decrease or be 1/4 what it was originally. And so let's go ahead and write that out. The new intensity of the light will be 1/4 of the intensity when we double the distance. Right, so I explained the meaning of that. Looking at that intensity thing, you could also express it as 1/4 times k over d squared, right? That's the same thing as k over 4d squared. So whatever that value is, it's going to get multiplied by 1/4 when the distance is doubled. The last type of variation we want to look at is combined and joint variations of variables. This is where we don't just have one variable, but 2 or more variables that have a relationship to some common, in this case, we're going to say z. So there's a lot of variety that can come with these joint combined variations. For example, the expression z varies jointly as x and y means z is equal to some k xy for some non-zero constant k. So just direct jointly, we have 2 variables, x and y. We have some constant k here equaling z. Similarly, if we can also have powers. If m and n are positive numbers, then the expression y varies jointly as the nth power of x, and the mth power of y means k n x to the n, y to the m for some non-zero constant k. So you can even have powers in there. And also, it doesn't really say this here, but you can also have inverse variations mixed up with direct variations. So you have to be really careful as you read it. Let's go ahead and look at an example here. And one of the examples is Newton's law of universal gravitation. And so we're going to kind of come up with this or look at this based on the description that we have, which can get complicated, so we need to look at this carefully, read it carefully, sometimes many, many times over. Newton's law of universal gravitation says that every object in the universe attracts every other object with a force acting along the line of center of the 2 objects. Also, this attracting force is directly proportional. So here we have a description of a direct proportionality. Directly proportional to the product of the 2 masses. So these 2 objects will have masses. So we'll label one as M1 and M2, mass of 2 objects. And inversely proportional to the square of the distance between the 2 objects. So M1 and M2 will have a distance. So that, of course, we'll just label with D, but it's going to be the square, and notice that it's an inverse variation. Okay. So how do we write this out symbolically? Let's go back and reread this again. We need to come up with our other variables here. Newton's law of universal gravitation, okay, that's just the name of the thing, says, the formula says that every object in the universe attracts every other object with a force. So there's some sort of force that we're looking for, acting along the line of center of the two objects. So I'm going to put F, because this force is the formula that we're really trying to find here. And it varies directly with the masses. So I'm going to put the product of the masses. Let's see, let's go back. Force acting along the line, so that's just acting on the line of the center of the two objects. This attracting force, so the force is directly proportional to the product of the two masses. Product meaning the multiplication of the two masses. So I'm going to say K, right? This is my general thing here. K times M1 multiplied by M2. So this is my direct proportionality. Right? And it's a joint one because we have two masses there. So two different variables that could be. And then we add to that description an inverse proportionality to the square of the distance between the two objects. So inverse relationship means it's going to go in the denominator. So we're going to have D squared down here. And this pretty much is going to be my formula. We have a force. It's directly proportional to the product of the masses. So we're multiplying all three of these basically. And then inversely proportional to the square of the distance. The inverse tells me we've got something in a denominator, and it's the square of the distance between the two objects. So D is the distance between the two objects. I probably should have written that down so we know what D is representing. Distance between objects, which we're going to square, but D itself is representing simply the distance between the two. And here we can actually look at the actual formula. You'll notice that the K kind of went away and we just have G, because they didn't give us any numbers there again. They were just giving us a description that we wanted to come up with this formula for. So here we have two objects. It looks like kind of an Earth and a moon, or a sun and a planet, or something big. But this universal law of attraction actually applies to every object, doesn't just apply to large objects. But you can see kind of our things here. Instead of D, they used R, which is the distance between the center of the objects. So we see that here. Again, we just took out a different variable there. But we picked similar variables with the masses, and then there is a K there. It's understood because it's been found, right? In the same way that we find all these things. We take an example and we use it to calculate G. So G is something that never changes. It's a constant value, and it's called the universal gravitational constant. And it's approximately 6.67 times 10 to the negative 11 cubic meters per kilogram per second squared. Again, kind of a difficult to understand value there, but that's what it is. And so for any problem, if we know the two masses, we know the distances between them, we can calculate the force of gravity on those. So you can see that both direct, inverse, joint, all of these variations have this idea of proportionality to them. Sometimes as one gets larger, the other increases as well. Sometimes as one gets larger, one decreases in value. We saw that with the inverse proportionality. And then we can have a lot of other things, joint and compound relationships, some of which are proportional. So if they're proportional, we're multiplying them. If they're inverse, then we're dividing by them. And this covers a lot of different just formulas that we have out there, dealing with volume, dealing with area, a lot of geometric type of relationships. And so now you're going to go practice some of these. Remember the 4 steps. First, identify the type of relationship. Second, find the K value. Third, substitute the K value into your formula. And then fourth, solve for the ultimate question or ultimate portion of the question, the unknown, when one of the variables is something else. Good luck.